So, welcome to the afternoon session. So, we're very happy to have Professor Cumrun Vafa today talking us about
We're talking about mirror symmetry.
Yeah.
Old and new, right? Okay. First of all, thanks for inviting me to attend this conference. It's a pleasure to give a talk here today, reminiscing about those old days and the kind of. It's also interesting for me to remind myself of the path that my research took in the past, whatever decades, in the direction connecting to some certain mathematical aspects of string theory, specifically having to do with the concatenation of strings on Calabi-Yau. So I'm going to just kind of remind myself of what kind of things led me to do what I did in terms of my interest. I'm not going to be comprehensive in terms of other people's work, so by no means view this as a review of the literature or anything like that. That's not my intention. I'm just going to say it's a personal view of how I got to think about mirror symmetry and so on over the years. So I first start with what was the in mid 80s string theory came to be prominent, and many people in high energy theory directed their attention to it, and we were all excited about the bizarre or new world of string theory. And we were learning some amazing stuff which didn't make much sense to the non-string theory picture of the world. And one of the prime ones which caught the attention of many people was the duality, which takes a circle of radius r and says that there is no difference for string theory whether the circle is of radius r or 1 over r. This fact was quite amazing, and the surprising thing was that this was easy to prove. It was a trivial kind of a thing you could actually prove this. It wasn't like a bizarre thing, but from a point particle perspective, it was mind-boggling. How could you relate a circle of size radius r with a circle of radius 1 over r? It cannot be. You could send a light around it and measure the distance. Circumference is a geometrical invariant. So what do you mean? And so forth. So how do you reformulate your way of thinking about the physics? If Einstein said, well, I can measure the radius by sending a light around and see how long it takes to come back, how could it not distinguish this with that? And the answer to that question, if Einstein raised that question, the answer would be there are two different photons. One of the photons made of the usual photons, and the other ones will measure the 1 over r as the radius. So there are two photons, and that's the physics answer, which is bizarre from a field theory viewpoint of why Einstein would be wrong to say that there's only one radius. So this kind of picture was really, bothering us and telling us that our notion of geometry is false. Our notion of what is geometric invariant is incorrect. Just this very simple example. And this was the beginning of a lot of things that I began to think in connection with geometry and string theory. This one we really understood. There was no doubt. There was no funny stuff. We could actually really understand what's going on, both physically and mathematically. Now, but the connection between geometry and field theory took a while to kind of get more advanced at this level. And part of the beginning of advancement came with understanding conformal field theories, which was the bread and butter of two-dimensional worksheet of strings, so 2D CFTs specifically. So in the context of 2D CFT, there are various types classified by the central charge. For example, for the usual conformal field theory with no particular supersymmetry, for C between 0 and 1, there's a discrete set of possible values, and these values are consistent with unitarity and all that were already classified by physicists, what's called the minimal models. And Zamolodchikov connected some classes of them to bosonic theories with potential phi to the 2p. So kind of a Landau-Ginzburg model with the potential phi to the 2p, and it connected these two minimal models for the diagonal series. This was for the case with no supersymmetry, and people had also studied the cases with more supersymmetry. And the reason more supersymmetry were interesting is because we were interested in the compactation of string theory, which gave us supersymmetry, and therefore objects like Calabi-Yau or geometries which have covariantly constant spinors were crucial for us in string theory, and people began studying those. In those contexts, we got more specific, more specialized kinds of conformal field theories, For example, for Calabi-Yau, specifically threefolds, which is the particular case of interest for us for supersymmetry coming from 10 dimension to 4, we ended up with what's called the 2, 2 supersymmetric theories, 2 left moving and 2 right moving supersymmetries. And people had studied, had already considered minimal models for them. And in that case, again, this corresponding C hat, the central charge of the algebra, between 0 and 1 give you a minimal model. And it was classified. It was already classified that the minimal model classification followed a pattern called ADE, which a priori had nothing to do with the ADE of geometry, but it has some remnant of how you construct these modular invariant partition functions. So my first connection with this kind of connecting this conformal field theory geometry was generalizing what Zamolodchikov had done to try to understand what these mean geometrically. And this is the work we did with Warner, and also independently Martinek did a similar thing independently. And we found that the corresponding replacement of potential is superpotential. And we got the series where you have different, the A series would correspond to one variable, one field superpotential, the 2 series with 2, and then the 3 exceptional ones corresponding the singularities that correspond to the familiar singularities of ADE. And of course, you can add Z squared to them. So these give you the ADE on the nose. And we found that these seem to correspond to these minimal models. However, we were luckier in some sense than Zamolodchikov's case, because in the case of Zamolodchikov, he could only give heuristic arguments why this is the case. For us, because of supersymmetry, certain things did not get corrected. And we can actually check some exact things in this one and see that those exact things are correctly realized in the minimal model. So we gave very strong evidence that this is the right picture from this picture. So it became clear that we now really have a dictionary between conformal field theory, which is an algebraic data, and geometry, which looks now like geometry. So we can now rephrase these in this language. Then came Gepner. The order, I'm not exactly sure which order, but at any rate, he studied, again, minimal models with this much supersymmetry. And he said that, well, if you want the Calabi-Yau threefold, the corresponding C hat is equal to 3. But these are less than 1, between 0 and 1. So what he did, he took a bunch of these guys to add them to 3, tensor them together, and out of that made what could be looked like a Calabi-Yau compactification, even if it was nothing to do with Calabi-Yau per se. It sounded like you just take a bunch of these simple models and put them together, and you have a conformal field theory, which mimics everything you want to know for Calabi-Yau, but not actually, there's no geometry associated with it, just abstractly, algebraically is the same. Then we were able to connect that picture using this kind of map to actual geometry. So in other words, for example, he had taken a model which we took, which we identified with W x to the 5th. He had said that if you take 5 of those, each one of them had central charge 3/5. If you take 5 of those, which we then would say corresponds to this, and put them together, he gets the same numbers as quintic, for example. There are some order faults here he had to do with Z5 and all that, but that's not, I'm not trying to emphasize that part. But the main point was, from this algebraic data and this connection with geometry, we could see that what he was doing in some sense was just, can be translated into something purely geometric. Now, my thinking on the subject got dramatically refined or changed in '89 because of the work we did with Lecha Warner. And what we were trying to do in there was to try to understand these theories better, taking into account the fact that they are sometimes nicely geometrically realized, and the fact that there's a natural ring which goes with the singularity with this kind of a potential. So you look at the ring which was generated by the variables that you have, modulo the ideal generated by dw. And this ring was very special for not only the singularity theory, but also from the conformal field theory. This ring turns out to be the ring of the actual operators that you can multiply and gives you this ring. So it had meaning in that language as well. So we try to understand these theories, and these rings, these elements and the ring, etc., play the same role as cohomologies and the ring cohomology ring in general geometric setup. So we're trying to understand the meaning of these rings. So we found, okay, so in these kinds of cases, we identified the corresponding rings of these guys with cohomology rings. So we said, okay, if you're given an abstract 2,2 algebraic data in the form of conformal field theory, we can read off the cohomology ring of the manifold. But the problem was we got two different rings, and we did not know what to do with it. What were the two different rings? Well, the algebraic data we had was 2,2 supersymmetry, which means that we had the energy momentum tensor for the left movers and right movers. We had two supercharges for left and right, and we have a U1 charge for the left and right. So this is the left side, which is then equal to 2, and this is the right side. Depending on the relation between the dimension of the operators and the charges, the rings behave differently. They look formally the same kind, but we had an ambiguity, we call this right. We had an ambiguity which had to do with flipping the sign of one charge relative to the other one. So if you flip the charge sign of the charge from the left versus the right, you flip these two rings. So these rings we call the CC ring and the AC ring. Namely, chiral ring and anti-chiral ring, depending on whether you choose the plus sign or minus sign flipped. And both of them behave as if they are cohomology rings. So for the same conformal field theory, we had two rings playing the cohomology ring. That didn't make sense. Because if you have a geometry, there's only one cohomology ring. What's the other ring? Of course, in the context of a specific Calabi-Yau, we could look at, say, oh, one of them ring has to do with the variation of high structure rings that we can define, and the other one is the usual cohomology ring. So we understood that it can be translated into specific cases, but from the geometrical data, neither one is more fundamental than the other. They were on the same footing. We couldn't say, this is the cohomology and the other one is something else. No, we had no choice. So therefore, we really had an ambiguity. And so we said, if there's an ambiguity, that means there's an ambiguity in the space itself. Why? Because we already knew this. We already knew these examples existed. We already knew that R goes to one of our symmetry, so therefore it was not surprising. We said, okay, same thing happens there, so why not here? That means that you just said that same conformal field has two different realizations, where one ring or the other ring plays a role of cohomology depending on which manifold you have. Before we wrote this paper up, we noticed that it flips the Euler characteristics of Calabi-Yau. And so I remember going and asking Yao about this thing that we are making a prediction that for every Calabi-Yau with chi, there's one with minus chi. And he was very surprised because he said, we know much more negative Euler characteristics of Calabi-Yau than positive. So he said, that doesn't sound right. So from the viewpoint of the no geometry at that time or the examples, this conjecture sounds completely off the right track. Nevertheless, this was so obvious that we made this conjecture, nevertheless, in our paper, with, you could say, 0 examples. Because the idea was kind of very natural and had to be somewhat similar to these. So we make that statement that for every Calabi-Yau, there's another one with the opposite problem, with the chi flip. Okay. It was for any Calabi-Yau, because any Calabi-Yau gives you 2,2. K3, for example, gives you 4,4, but 2,2 is a subalgebra of it. So any Calabi-Yau gives you 2, at least. So the statement was for any endpoint. And we stated it like that. We didn't say it only for Calabi-Yau 3. So this is actually a lesson, actually. The reason I'm emphasizing is that one should not lose heart if something is natural, even if there's little example, or even if there's example against it. I mean, quote unquote example against it, not obvious example, but it felt like the currents were running in the opposite direction. but the idea was sufficiently simple and sound that it didn't bother us. Okay, then, good. Then came a work that Green and Plesser did. Green was a postdoc at Harvard, and Plesser was my student, and they were trying to realize examples of this kind of situation where they fit. So, what the important thing they realized is that if you take the minimum model that I just told you, the simple minimum model, they notice that if you quotient it by Zn, it's a Zn symmetry, you can quotient it without doing anything. You already know it should be x to the n. Why is that? Well, because the central charge of this theory is fixed in terms of this data, and quotienting this out cannot give you anything other than that central charge. And therefore, it must be, if there's other D and E not there, then it must be that A series again. And indeed, this was realized to another W, which is a different, which is equivalent to another minimum, same minimum model, but just reform it. In other words, quotienting this out gives you back the same theory with a different variable. However, what they noticed there is that the CC ring here disappears on this one and becomes the AC ring here. So the CC and AC flips. Just for this minimum model with not much difficulty. This was easy to prove. This was a simple line to prove. So they proved that easily. And then what they did was to notice that, oh, we can actually take copies like Gepner did, put them together, and take their quotient, and then apply the quotient and get a mirror of this in the same sense, just by using this as the building block. And that's what gave rise to a huge number of these examples, which therefore was the beginning of concrete examples for mirror symmetry. And then, of course, people try to take a large number of these hypersurfaces and other things and study the corresponding Euler characteristic when you do these kind of quotients. And they find that the number of available things versus Euler characteristics is almost symmetric now. When it did a lot of it, not exactly, but it was very essentially. So people begin to gain confidence in the idea that they come essentially equal numbers, pi and minus pi. And now there was concrete examples, and therefore it began to be believed. Until, of course, more than the belief was the work by Candidas et al. In 1991, where Candidas et al. Actually used this, put this to beautiful use, where they could actually use these, the mirror symmetry, to actually compute aspects of one ring from the other ring. One ring, which is the homology ring, which gets quantum corrected by the Lorentz instantons or Gromov invariance, gets related to the other ring, which doesn't get corrected. And so therefore, by computing these mirror cases, you could gain insight and compute very difficult things, like with geometry, as you all know, gets related to these beautiful issues involving variation of part structure. Now, there were examples of mirror symmetry that we understood very clearly from the beginning. So the first example was P2, the Calabi-Yau one dimension, which was mirror to itself, where the Kähler and complex structures got flipped here. You just flip them. And this we understood, and this was the simplest example of mirror symmetry, which is actually a special case of T-duality, the duality I started the discussion, where you basically start with the product of the two circles, and you take one of the circles to go to 1 over itself. And just this simple example for a rectangular torus already illustrates this mirror symmetry simply. So this particular example of mirror symmetry, we already understood from early days that nothing amazing, but well, it's already amazing, but still it's something related to already T-duality. So T-duality or Argos 1 over R gave you already a simple example of the complex dimension 1 case. That's mirror symmetry. Now, I'm going to mix and match both the theory and also the application of mirror symmetry. I will now give you one example of the application of the mirror symmetry, which we did in '95. This was actually related to a different motivation. What we were trying to do was trying to study. So we were studying the quantum field theory question in 4 dimensions, supersymmetric field theories like n equals to 4 supersymmetric angle. And we wanted to understand properties of this theory, and there was a symmetry in this theory called Olive-Montana duality, which said that if you study n equals to 4 angles with a gauge group, you get a dual gauge group, which is in this mathematical called Lang-Lang dual group. Corresponding to that one, there's this transformation happens when you go from weak coupling to strong coupling. So there's a transformation, there's a coupling constant like same as parameterized the moduli of the torus, which is flips when you go from a group to the dual group. Now, we wanted to understand this as much as we could. What we did was to study this theory and put it on a Riemann surface down to 2 dimensions. In 2 dimensions, what you ended up getting is a sigma model, similar to the sigma models that we did in Calabi-Yau. And we found that the Calabi-Yau that you get, instead of Calabi-Yau, it's actually a hyperkähler, which is the Hitchin moduli space of the Hitchin space, corresponding to that group. So the analog of the Calabi-Yau was replaced by the Hitchin moduli space, which has more structure than Calabi-Yau because it's hyperkähler. Now, this hyperkähler geometry has a toroidal fibration. It's a Jacobian variety of toroidal fibration. And we applied the mirror symmetry for T-duality to the Jacobian fibers. And we found that what that gave rise to was actually the corresponding dual group. So we found that T-duality of the fiber, of the toroidal fiber, applied fiber by fiber to this geometry gives you the mirror symmetry between the moduli space of the Hitchin space group G with a dual group G. I believe that Tony was actually guiding us in our discussions there, probably if I remember correctly. Correct me if I'm mistaken. This was the work we did with, I think, Berchatsky, Johansson, and Sado in '95. But this was still special to the case that there was a natural Jacobian variety. There was a toroidal fiber in the game. So it screamed to be used as T-duality. That's what we do. In '96, Strominger, Yau, and Zaslow found this beautiful picture that this idea that you can do T-duality could apply to all Calabi-Yau. In some sense, viewing a toroidal fibration in essentially any Calabi-Yau with a T3 fibration, for example, or Tn fibration over an n-dimensional base, and applying the duality to the fiber. So this would generalize the one-dimensional case and n-dimensional case just by this kind of a picture. And this was a very natural interpretation of the fact that essentially everything boils down to T-duality, which was at any rate the motivation for many of us to try to even suggest mirrors. Any questions? However, this was not sufficient for the following reasons. What happened was already among one of the models that Gepner found for minimal models, he took 9 copies of a theory which has CH equals to 1/3. The theory with CH equals to 1/3 corresponds to W is equal to X cubed. He took 9 copies of this to get CH equal to 3 and made a Calabi-Yau out of it. So he wrote down the double. So then we would write down the corresponding object was x1 cubed up to x9 cubed, and he divided by z9, z3, I mean, acting on all 9. So he took this model and he said, this is an example of a Calabi-Yau. Tell me what geometry this is. Okay, this did not sound like a hypersurface in the wrong, to be hypersurface in the wrong space. This would not look like a Calabi-Yau. However, he was getting Calabi-Yau. So this is already when he suggested that, I pointed out to him that this actually has the same homology charge number as C2 times C2 times C2, modded by Z3 times Z3. So I told him that this will be exactly like this, as far as the cohomology classes go, except I need to flip some charges, some signs. In other words, what I was telling him is that this is the mirror of this. So in other words, he was giving a model for which I was telling him his mirror. But this mirror this guy is rigid, has no complex deformation. And therefore, the mirror guy is not going to be Calabi-Yau. But he was giving a mirror. So this showed that the mirror goes beyond the category of Calabi-Yau. At least the naive category of Calabi-Yau is not the right category to define mirror symmetry. And this was already the first example where we saw this. So if you want to formulate mirror symmetry to be more general, it's beyond, it generalizes the category of Calabi-Yau. Another example of this is that if you put an extra Z3 here, you can delete the Z3 from this side. And this will give you the Z overfold, the famous Z overfold that people studying the wild light as well. Okay. So I'll come back to this in a second. What's the resolution? How do we think about this? Now, this was now hitting us in the period where dualities in string theory have been discovered. And this is 95 period. People were studying mirror symmetry and we're studying these new dualities in string theory. And T-duality was kind of like a simple example by then that we kind of thought we understood. And these new dualities are far more amazing and far more remarkable properties that they have. And it made quite non-trivial predictions, and it allowed us to use the technology of mirror symmetry to good use. And I'll give you one example. So one thing we learned was that the ADE singularity correspond to ADE gauge groups. What does that mean? For example, if you take C2 modeled by subgroup ADE, subgroups of SU2, cyclic dihedral and exceptional subgroups, this corresponds, well, there will be singularities. When you blow it up, you get the Dinkin diagram of the corresponding ADE for the intersection of the blow-up cycles. And this turns out to be related to the fact that in this geometry, you're actually getting ADE gauge symmetry, having to do with the membranes wrapped around these two-dimensional cycles, which correspond to these two cycles of blown-up geometry. So there was a map between singularities and gauge symmetries. So you can geometrically engineer a gauge symmetry by singularities. So then, in various examples, we applied these, and we, for example, found that if you are interested in studying 4D n equal to 2, let's say, with SU2 gauge symmetry, suppose you were interested in studying the 4D n equal to 2 supersymmetric theories with SU2 gauge symmetry, the example that Seiberg and Whitten beautifully studied, if you wanted to study this kind of example, you could reformulate it geometrically in the context of Calabi-Yau. How do you do it? Well, you needed to get an SU2, so you needed an A1 singularity. A1 singularity basically means a P1, which is shrinking. And this is if you go down from 10 dimensions on a C2 mod A1, you go down to 6 dimension. So by the time you put this cotangent of P1, you're down to 6 dimension. Now you want to go down to 4 dimension. If you put it on T2, you get n equals to 4, but you want to kill it by half, so you need another P1. You need to fiber this another P1. The simplest one is just a product structure, P1 times P1. So if you took a geometry where you have a P1 times P1 with O minus 2, comma minus 2 line bundled over it to give you a local geometry of Calabi-Yau, you have realized the n equal to 2 SU2 gauge symmetry in 4 dimensions. So now we are translating data from physics of field theories, forget about string theory, field theories in 4D to geometries of Calabi-Yau. Now, what is that good for? Well, it turns out you can now compute things that we did not know how to do using mirror symmetry in the following way. The idea is that the area of this P1, if you translate it to gauge theory language, there was the 1 over the gauge coupling constant of the Yang-Mills theory. And so the wrapping of the strings, or the worksheet diagram wrapping around this, which gives you factor e to the minus n times a if you wrap n times around this P1, correspond to e to the minus n over g squared. But n over g squared corrections to things in physics correspond to instanton corrections. So instantons are for the n equal to 2 Yang mills, but related to counting curves wrapping around this P1. And how do we compute that? Well, we use mirror symmetry. If you take this geometry and do mirror symmetry for this, you can easily sum this up. So we were able to actually use this to compute, using mirror symmetry, answers to questions involving gauge theory. This is one of the contexts in which I had a lot of interaction with Bob, who was also very interested in the mathematical underpinning of this local situation and how mirror symmetry works. In other words, it's not compact. The geometry is only a piece of a Calabi-Yau, but still you can define the notion of mirror symmetry, even in these local models. And he worked out the mathematical implications and meaning of what this local mirror symmetry means. Now, this was just an application of it, but then we tried to formalize this a bit more, understand how this works. And this is what we ended up doing with Puri, which was basically a way to formulate mirror symmetry. It was a mirror symmetry between complex plane and the Landau-Ginzburg theory. You take a complex plane, non-compact complex plane, X, and we said this is mirror to a theory with a Landau-Ginzburg potential e to the minus y. Where the mirror circle, so this is a complex plane, and the circle symmetry that corresponds to T duality was not fiber constant anymore, but actually just rotating of the plane. So this rotation of the plane is in some sense like circle duality, but it's not a fiber, it's not a constant. That's why you get a potential on the right side, which is e to the minus y. It's not a constant either over there. And we argued that if you study the complex plane, you're actually going to be equivalent to studying this theory with this W. Using this picture, and the fact that these examples involve toric geometries, using these torus actions, we are able to map all these mirror symmetries in those contexts to corresponding Landau-Ginzburg models. For example, if you took O minus 3 over P2 as a local geometry inside the Calabi-Yau, we found that you can get the corresponding Calabi-Yau in the form x1 cubed plus x2 cubed plus x3 cubed plus ax1, x2, x3 mod out by z3, where xi are these e to the minus yi. So this one we could actually prove using the same idea here. And we could also prove that the one I told you about with Gettner, that the 9 copies of cubic, we could now show that, well, I will come to that in a second, but before I say that, is that you notice that this is also like torus. If we actually viewed this as an equation defining the torus elliptic curve inside P2, and we were able to show why that corresponds to using the same W, but just changing whether the fundamental field is X or Y. So mirror symmetry in that case became just a reformulation of whether the right variable is X or Y, and that was it. There's nothing else. The W did not change. So the local mirror symmetry was a way for us to actually give an argument for mirror symmetry beyond the local case. So that was the key point. Understanding the local case, and then understanding that the change of variables is all that changed going from local to compact. And then we also generalized this to fact varieties and all that, not just the toric example and so on. So we gave a formulation of how you compute the mirror symmetry in these cases, and then applied it to these non-cubics that, for example, Gettner has, and we got the same formulas we had before. So now we have finally an explanation that all these mirrors involve at least a Landau-Ginzburg, including the ones for which there is no formal Calabi-Yau. So the Landau-Ginzburg way was a way of generalizing that picture. You will always have the mirror symmetry in that category. And it's all formulated in terms of the analog of T duality, which in this case is just this statement, that the mirror of a complex plane is just exponential potential. That was basically the key ingredient. So I step back a little bit to talk about some other applications of these ideas. So one of the applications which is very dear to my heart was the work we did with Vershasky, Chakotay, and Oguri in '93. So, so of course, through the beautiful work of Candidos and collaborators, we already knew that the genus zero answer for Bowman invariance can be used, compute using mirror symmetry. Basically, you just go to the mirror guy and compute classical periods and so on, and you have the answer to anything you want to know for genus zero. And we were interested to answer the same questions of higher genus, genus one, genus two, etc. And the idea sounded simple enough. We want to compute the same thing using the easy side. We translate the hard side to the easy side. And we wanted to do it there. To our surprise, we found that the easy side, even though it was easier, it wasn't totally trivial. And because it involved a field theory computation, like computing determinants, it wasn't just a classical period. For example, at genus one, we found some generalization of Grace-Singer torsion kind of objects that we had to compute. And we tried to do it, and we managed to compute it. As our first example was trying to compute exactly determinants. We found that there's an analog of Cullen anomaly that is there, and you cannot just expect the answer to be purely holomorphic in the moduli. You mix them with the anti-holomorphic pieces, and this anomaly we solved, but it didn't quite get the full answer because we didn't know the holomorphic constant pieces that were there, and we were trying to find what they were. We had to go to the corners of moduli space to figure out what they were, and the way we did it was using mirror symmetry again. Namely, one corner we used A model, the other one the V model, and so on. So finally, we put them together to get an answer. So it was a hodgepodge of ideas from mirror symmetry, this and that, to get the answer for genus one and genus two, for example. And of course, that has now become quite. People have pushed it up to many more genus than we did. There are other applications. There are so many applications now that I'll just tell you a few of them, which are probably less familiar to people here, which I think I'm one of the things that I like about this bringing examples which are not familiar to people, because I think they should become more familiar, perhaps. One example is that suppose you're studying in 4 dimension, suppose you have a 4-dimensional real manifold, which has some elliptic vibration, rational elliptic surface, as an example. So some kind of, let's say, T2 fiber over something, some base. And what do you want to do in this case? Suppose you're interested in studying rank n bundles, and you want the moduli space of instantons. There's a study the moduli space of instantons of rank n bundle in this space. So what you want to compute the Euler characteristic of this moduli space, of this UN instanton on this space. You might think this has nothing to do with mirror symmetry, but actually using mirror symmetry, you can compute this. And why is that? Well, if you do the T duality, the rank n bundle for us corresponds to a 4 brane wrapped around this whole thing. So we call it D4 branes and D0 branes. And T duality maps this to D2 horizontal and vertical by doing the fiber T duality. So this question of boils down to the bound states of D2 and D2 brane horizontal and the fiber, which is what Cumrun computes, which you can use now mirror symmetry to compute. So by this chain of things, you can use mirror symmetry to compute things like this. So it's quite powerful, and we in fact use it for P2 Bournow at 9 point corresponding to rationality surface. We use that to compute, I think, ranks up to some rank, U2, for example, as U2 computed, and I agreed with what was predicted in math literature. There are other models. The A polynomial for nuts gets related to mirror symmetry. You study that in the context of trying to realize the Chern-Simons theory and the relation to nuts in the context of topological string. You can use that setup to map mirror symmetry in that context to A polynomial. A partial mirror symmetry in the context of Chern-Simons theory, if you don't apply it to all 3 dimensions, but 1 or 2 dimensions, maps this to works of Castello et al., which relates to integral systems. Another example of application of mirror symmetry. So the mirror symmetry has a lot of applications. However, I think that I don't want to just end with just reminiscing about old stuff. I want to say something that I'm actually thinking about now, for which I don't know the answer to. And I want to pose the questions to this audience so that you know that there are very interesting questions still open that are basically close to these kind of ideas. So let me pose my question. So I mean, these days I'm actually quite interested in the idea of what you can and cannot get from a consistent quantum gravity. For example, the number of compact Calabi-Yau threefolds or n-folds we think is finite. Do we have an argument? No. Do we believe it's finite? Yes. Why do we believe it? Well, mathematicians might have their reasoning, and physicists have their heuristic reasoning. We don't have a deep understanding. We think finiteness of quantum gravity implies finiteness of number of Calabi-Yau, but we don't have a proof. There are these kind of questions that are part of the program we call the swampland program to see what can or cannot happen. For example, can you have an arbitrary large Euler characteristic Calabi-Yau threefold which is compact? The answer is we think no. Proof, we don't have it. And so these are the kinds of questions that I think are crucial in understanding quantum gravity. Namely, the difference between compact versus non-compact. Non-compact, you can get a lot of things, almost anything you want. Compact is very difficult and you get finite. Like ADE singularities, there's no bound in what rank you can get. AN for arbitrary n you can get in a local non-compact singularity. But as part of the compact space, A3, there's only finite choices. This truncation from infinity to finite, this truncation is is an example of what we call the swampland program. Namely, a general n does not appear, only a few of them appear. Finite list that you know inside A3, and the generalization of these kind of questions. So we have come up with some of these heuristic arguments and ideas of what characterizes what is and what is not possible. And it's a very difficult problem, as you can imagine. But we try to apply these principles to the examples we know to see if it explains everything we know. And of course, it's going to be difficult to get everything we know, but we can try to get what we know. So we applied this to the cases that we know, and we came up with one question that no matter how much of these principles we use, we cannot rule out the existence of one possibility, which I'm going to tell you what prediction to make. It will correspond to having what we call a pure 5D n equals to 1 supergravity. Now, what would that mean? Well, just to orient you, if you take M theory in 11 dimensions and put it on a Calabi-Yau threefold, you get 5D n equals to 1. So this story is in the same category as Calabi-Yau threefold, so you're familiar with it. However, whenever you do this in the context of the Calabi-Yau, you always get a silly field, which does not allow you to get a pure supergravity. You get always has one hypermultiple. One extra field that gravity says, I don't need it. But Calabi-Yau says, no, you have it. You cannot avoid it. So where does this come from? This comes from the four corners of the Hodge diamond in the Calabi-Yau field. Those four fields combine to give you this multiple. You cannot get rid of it. It's part of the Calabi-Yau. Okay? So this is always there. And so the question we pose is, could you prove that this is a consistent theory? Can 5D n equals to 1 pure supergravity without this somehow not exist? Okay, that's our question. In other words, somebody might say, well, this has nothing to do with Calabi-Yau compactation. Somewhere else, somehow else, you might get it. It could be a consistent physical theory. Forget about Calabi-Yau. Who cares about Calabi-Yau? But is it possible that no, really, there's a good reason that physics cannot get this either? That's the kind of question we want to understand. Is that clear? So if you say there is no hypermultiplet, in fact, this is what we call the universal hypermultiplet, which comes from the four corners. There are other hypermultiplets which come from complex structure deformation of Calabi-Yau. We don't want that either. So it looks like a rigid Calabi-Yau, which doesn't have the corners, which at least doesn't have the H30. But that, of course, is not a Calabi-Yau. But nevertheless, it looks like that. So what we tried to do, and we didn't quite manage to complete it, is that we said, suppose you go down to 4 dimensions. If you go down to 4 dimensions, this corresponds to n equal to 2 in 4 dimensions, which we are familiar with. what do you get in 4D? You just get one vector multiplier, which in the language that you're familiar with, this corresponds to Calabi-Yau with one scalar moduli. So suppose somebody told you that there's a Calabi-Yau with one scalar moduli and no complex moduli, and worse than that, no H3 zero. Okay, that's what we're after. Now you say, how can I even test such a thing, that they exist or not? And the question would be that, well, you have a topological string, which you know how it starts. For example, you have S0, which comes CT cubed, the triple intersections, plus the CTT, and then there's a chi times zeta of 3, and so on, plus exponential corrections. You know that this structure will still be true from gravity arguments, even for this. And now you also know that the chi that this you would need is chi 4, with only one scalar moduli. Of course, there is no Calabi-Yau with chi equals to 4 with one scalar moduli. All the Calabi will have chi less than 4, because the hypermodulus or the other one will correct it the other direction. So this should not exist. You should not be having a Calabi-Yau with only one scalar moduli with these chi's. Now, people have written down things like the prepotential which satisfy the Picard-Fuchs equation from Picard-Fuchs equation, which seems okay, but it cannot be complete, we believe. So most of them, I think, cannot be complete. They cannot come from Calabi-Yau for sure. But the question is that if you formulate all the FGs with all the properties that you think a would-be Calabi-Yau should have, could this belong to that list? If you formulate all the consistency conditions that you believe any FG should have, can you formulate it and see if there is a solution which has this kind of property? If you do, then it at least gives evidence that this may exist. If you find no, there is a problem with this, it might suggest that this may not exist. So understanding and formulating consistency conditions for would-be Calabi-Yau structures, regardless of whether there is a Calabi-Yau, is a crucial question. And that's one of the areas that I'm working on today.